right, so last one. So I want to look at now polarized objects. Okay, so I want to look at, say, bar electric. So an electret is something that has a polarization even when it's not in a field, and its polarization is approximately that of what it originally had even when it is not in that field, even when it is in the field, because even though there will be some induced polarization like we talked about last time, it's small compared to the magnitude of the polarization that it has without the induced polarization. And that's going to make us, or that's going to give us some more useful things. All right, so what we'll say here is that polarized objects feel a force only from non-uniform fields. Okay, and so what that means is if I have that bar that I had in the last lecture, seen there, being polarized, it will attract something that is polarized, the bar electric, or something with the induced polarization. Both are true. It'll attract that because there's a difference in the fields at those points. So because this is polarized, right, there's a charge here, Q, and there's a charge down there, minus Q. And because of that, if this is a uniform field, those two things are going to cancel out. All right. And so we may as well write that down. A polarized objects feel no force from uniform fields. Okay, so you have to have this non-uniform field going there. So that's part of the reason why if you rub a, if you were to rub a big plate of amber with sheep's wool, you wouldn't be able to pick things up with it. It has to be a rod or something like this, because you get this non-uniform force that gets stronger and stronger. These arrows get closer and closer together. These field lines get closer and closer together as it comes up towards this bar, so that thing's getting stronger and stronger. The force is getting stronger and stronger. Now in this case, because you have the positive charge up here, closer here, that's got a stronger force pushing down than this guy who's got the negative charge farther away that's being pulled up. So the force is going to come down. In this case, the force on this bar electric, excuse me, with a T. It's like magnet, but with an elec instead of a mag in the front. So that force is going to be equal to Q times E on top minus Q times E on the bottom. And in some situations, these arrows, these directions for the fields could be useful. So if this was at a funny angle over here, then we'd have to take into account that angle. Or not the angle, but the actual positions, because the angle is not quite enough. Depends on how long it is, but it's not quite enough. But another question you might have after that is, what happens if this guy's in a uniform field? Does anything happen to it? Well, sure, something does happen to it, right? If this guy's in a field that's uniform like this, right? And this is positive Q over here, and this is minus Q over here, then this is going to be pushing down this way, right? And this is going to be pulling up this way. It doesn't feel a force because these two forces are the same and they cancel. But what does happen? Well, it starts to spin around the center of mass. Right? So this force is pushing, I have no idea which way it is for you, right? Let's say it's pushing counterclockwise for you, and this one's pushing counterclockwise for you as well, right? So it's going to spin around like this. Right? Even though it's not going to be pulled towards the source, it'll start spinning around in space. Isn't that fun? Right? So it's going to whoosh, 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 whoosh. But, you know, we can talk about that if we really care about oscillations. Do you? Tell me if you do. No, that's right. Looks like a D, so it must be a B. So we just said is a polarized object. Feels a torque. From a uniform field. Could be zero, but probably not. Okay. I mean, it could be aligned like this. This one's aligned, so there's no torque on it. This one's not aligned, so there is a torque. Right? But I mean, if you just take a random field and you take a random object and you put them in a space randomly, they're almost certain to be not aligned, right? So formula for that is the torque is equal to the polarization times the the electric field, so the magnitude of the polarization here times the magnitude of this electric field out here times the sine of the angle between them. Right? This is the angle between P and D. So in this case, there is no angle between them. It's zero, so there's no torque. In this case, it's 90 degrees, so it's maximum torque. All right? So that's all we do for charged objects. And I think that's about it for fields. I think we have 4 lectures per unit. So we need to get into potentials and electromagnetic energy, or electrostatic energy. So we'll talk a little bit about electrostatic energy next time. And that will prepare us for Module 2. And Module 2 will be simple circuits, currents and circuits, simple things in the sort of quasi-static approximation. Hopefully that'll be good enough for us. Right? Thank you very much for listening. I will talk to you next time.